Hi everyone. Today we're doing notes for 5.2 binomial probabilities. So features of a binomial experiment. There is a fixed number of trials. We denote this number by the letter n. The n trials are independent and repeated under identical conditions. Each trial has only two outcomes, success denoted by S and failure denoted by F. For each individual trial, the probability of success is the same. We denote the probability of success by P and that of failure by Q. Since each trial results in either success or failure, P plus Q equals 1, and Q is equal to 1 minus P. The essential problem of a binomial experiment is to find the probability of R successes out of N trials. According to the textbook of medical physiology, 9% of the population has blood type B. Suppose we choose 18 people at random from the population and test the blood type of each. What is the probability that 3 of these people have blood type B? Note, independence is approximated because 18 people is an extremely small sample with respect to the entire population. So A says, in this experiment, we are observing whether or not a person has type B blood. We will say we have a success if the person has type B blood. What is a failure? So a failure is going to be when a person does not have type B blood. The probability of success is 0.09 since 9% of the population has type B blood. What is the probability of failure? Please find this. So we know these need to add up to 1. So I'm going to do 1 minus 0.09. So this will be 0.91. How many trials N are there in this experiment? We have 18 people. So that means our N is 18. We wish to compute the probability of 3 successes out of 18 trials. What is R? So remember, R represents the number of successes. N represents the number of trials. So R is going to be 3. The central problem of a binomial experiment is finding the probability of R successes out of N trials. So suppose you are taking a timed final exam. You have 3 multiple choice questions left to do. Each question has 4 suggested answers and only one of the answers is correct. You have only 5 seconds left to do these 3 questions, so you decide to mark answers on the answer sheet without even reading the questions. Assuming that your answers are randomly selected, what is the probability that you get 0, 1, 2, or all 3 questions correct? So this is a binomial experiment. Each question can be thought of as a trial. So there are n equals, it says here, 3 multiple choice questions left, right? So n equals 3 trials. The possible outcomes on each trial are success S, indicating a correct response, or failure F, meaning a wrong answer. These trials are independent. The outcome of any one trial does not affect the outcome of the others. What is the probability of success on any one question? There should be 2 words, any one, sorry. Since you are guessing and there are 4 answers from which to select, the probability of a correct answer is P equals 0.25. Probability of a wrong answer is then Q equals 0.75. In short, we have a binomial experiment with n equals 3. P equals 0.25, and Q, which equals 1 minus P, is equal to 0.75. Again, there are 4 answers, so this P comes from 1/4, and this Q, or 1 minus P, is 3/4. Now, what are the possible outcomes in terms of success or failure for these 3 trials? Let's use the notation SSF to mean success on the first question, success on the second, and failure on the third. There are 8 possible combinations of S's and F's. So I'll write these out. We can have SSS, SSF, SFS, SFF, FSS, FSF, FFS, and F, F, F. To compute the probability of each outcome, we can use the multiplication law because the trials are independent. For instance, the probability of success on the first two questions and failure on the last is, so I want the probability of success, success, failure. We can do 0.25 times 0.25 times 0.75, and this gives us 0.0469. We can continue on this way to compute the probability of R successes out of 3 trials for R equals 0, 1, 2, or 3. However, as n gets larger, we need to use the formula to compute binomial probabilities. So here's our formula. And this is going to be where n is our number of binomial trials, p is the probability of success on each trial, q is 1 minus p, probability of failure, and r is the random variable representing the number of successes out of n trials. If you notice this NCR, that looks familiar. That's our combination formula, okay? So we use that as our coefficient in front, and then we're multiplying by p to the r power, q to the n minus r power, and then this is what it looks like with the full formula. So practice 2 says, privacy is a concern for many users of the internet. One survey showed that 59% of internet users are somewhat concerned about the confidentiality of their email. Based on this information, what is the probability that for a random sample of 10 internet users, 6 are concerned about the privacy of their email? So we have 59% are somewhat concerned. So that means our P is 0.59. Our Q is 1 minus P, so that's going to be 0.41. Our N is equal to 10 because we have a sample of 10 internet users. And we want to know what's the probability that 6 are concerned. So R is equal to 6. So let's plug this in the formula we have right here. So this is going to be 10C6 times 0.59 to the 6th power times 0.41 to the 4th power. And then when we calculate this, we should get 0.2503. Okay, here's our next one. A rarely performed and somewhat risky eye operation is known to be successful in restoring the eyesight of 30% of the patients who undergo the operation. A team of surgeons has developed a new technique for this operation that has been successful in 4 of 6 operations. Does it seem likely that the new technique is much better than the old? We'll use the binomial probability distribution to answer this question. We'll compute the probability of at least 4 successes in 6 trials for the old technique. Each operation is a binomial trial, so let's fill this in. Our N is 6, right, because this is our trials. Our P is going to be 0.3. Our Q is 1 minus P, so this is going to be 0.7. And our R, this is going to be our 4. Okay. And remember, this represents the successes. Find P of 4. So let's use our formula from above. We have 6C4 times 0.3 to the 4th power times 0.7 to the 2nd power, because if we have 4 successes, that means we have 2 failures. And go ahead and find this, please. Okay, this should come out to give you 0.0595. Now I want to compute the probability of at least 4 successes out of the 6 trials. So remember, we can do this as the probability of 4 plus probability of 5 plus probability of 6. So we found the probability of 4, right? That's what this was up here. So our probability of 5, we're going to do 6C5 times 0.3 to the 5th times 0.7 to the 1st. This will come out to be 0.0102. Probability of 6 we're going to do 6c6 times 0.3 to the 6th times 0.7 to the 0 power. This one comes out to be 0.0007. So if I want the probability that r is greater than or equal to 4, we're going to add these three together. So this one, and this one. So 4, 5, and 6. So you have 0.0595 plus 0.0102 plus 0.0007. And this will give us 0.0704. So under the older operation technique, the probability that at least 4 patients out of 6 regain their eyesight is 0.0704. Does it seem the new technique is better than the old? Would you encourage the surgeon team to do more work on the new technique? So either this is a rare event, so it could be the same, or the new method is better. Okay. What does the binomial probability distribution tell us? When a binomial probability distribution is used, we know that the sample space of events consists of a fixed number n of binomial trials. This means the trials are independent and performed under the same conditions. There are only 2 outcomes for each trial, success and failure. The probability of success on each trial is the same and is designated P. Probability of failure on each trial is designated as Q, which is 1 minus P. The binomial probability distribution gives the values P of R, the probability of R successes out of the n trials for each R between and including 0 and n. And the calculation of P of R depends on the probability P of successes on each trial, the value of R, and the value of n. So now we can also do these on the calculator. So if we hit the distribution key, so this is going to be this distribution key. In order to do this, you hit second and then the VARS button, second VARS. It's right underneath the up, down, left, and right buttons. That'll take you to the distribution menu. Now, there are 2 different things you can do here. One, binomial PDF. This is going to look like this one. This is if you're doing P is going to give you the exact probability. So when you want, for example, the P that R is equal to 4. The other option that we have on here is binomial CDF. And for CDF, it's this one. This is for, C tells you cumulative probability. So P of R is less than or equal to 4. Okay, so I'm going to show you, I'm going to go back and show you how to type these into the calculator. So for B here, if I wanted to do this in the calculator, again, 6, this is our trials or our N. 4 is our successes. This is also your X value for the calculator. So if I wanted to do this one, I would do binomial PDF, and then I'm going to put in 6, 0.3, and 4. And that comes out to the same thing, 0.0595. Now, if I wanted to do the cumulative probability, so for this one, we can see that we have R is greater than or equal to 4. So remember, if I'm doing this, this is equal to 1 minus the probability that R is less than or equal to 3. So for this one, I would do 1 minus binomial CDF of 6.33. And that's going to also give us the same answer, 0.07047. Down below here is just a summary of different English expressions that correspond to tell you if you're looking for greater than or equal to, or less than or equal to. We're also going to go over additional properties of the binomial distribution, which is 5.3 today. So how to compute mu and sigma for a binomial distribution. Mu is equal to n times p. This is the expected number of successes for the random variable r. Remember, expected value is equal to the mean. Sigma equals n times p times q, or and the square root of that, or the square root of n times p times 1 minus p, and that's our standard deviation for the random variable r. So this is where r is the random variable, n is trials, p is probability of success, and q, or 1 minus p, is the probability of failure. So when Jim shoots field goals in basketball games, the probability that he makes a shot is only 0.5. The mean of the binomial distribution is the expected value of r successes out of n trials. Out of 6 throws, what is the expected number of goals Jim will make? So we know our p is 0.5 and our n is 6. So mu is equal to n times p. 6 times 0.5 will give us 3. For 6 trials, what's the standard deviation of the binomial distribution of the number of successful field goals Jim makes? Well, sigma is equal to square root of n times p times 1 minus p. So square root of 6 times 0.5 times 0.5. So this is the square root of 1.5, which will give us 1.22 for the standard deviation. Chebyshev's theorem says that no matter what the data distribution looks like, at least 75% of the data will fall within 2 standard deviations of the mean. As we'll see in Chapter 6, when the distribution is mound-shaped and symmetric, about 95% of the data are within 2 standard deviations of the mean. Data values beyond 2 standard deviations from the mean are less common than those closer to the mean. In fact, one indicator that the data value might be an outlier is that it's more than 2.5 standard deviations from the mean. So for a binomial distribution, it is unusual for the number of successes r to be higher than mu plus 2.5 times sigma, or lower than mu minus 2.5 times sigma. All right, consider a binomial experiment where n equals 20 trials and p equals 0.4. A says find the expected value and standard deviation of the distribution. Please do this. Okay, our mu, or expected value, or mean, is n times p, which is 20 times 0.4, which is 8. Our sigma is going to be the square root of n times p times 1 minus p. So this is square root of 20 times 0.4 times 0.6. And so this is going to give us 2.191, or this is about 2. So it says, would it be unusual to obtain fewer than 3 successes? Explain. Well, we have mu minus 2.5 times our sigma. So 8 minus 2.5 times 2.191. So that's going to give us 2.5225, which is about 3 if we're rounding it up to whole numbers here, right? So we want to think about if this is unusual. So let's check with 2 just so we can see. So I could also do 8 minus 2.5 times 2, which gives us 3, right? So if I do it using the whole number, we see this is 3, 2.5225 would also round up to 3. So would it be unusual to obtain fewer than those 3 successes? Yes, this is unusual. But it is possible. Okay. If we wanted to calculate the other side to get what our bounds would be for unusual values, 8 plus 2.5 times 2, if I'm using the whole number, the about 2 here, is going to give us 13. So anything from 3 to 13, anything within there would be considered normal. Anything outside that range would be considered an outlier. And that's where we're going to stop for today.